Hey gang, so in this video we're going to talk about the idea of a combination, which is a type of counting technique. And this shows up in a couple contexts. In one context we've got it in terms of sampling, which would put it in chapter 1, but we're also going to see it in another statistical technique in experience 5. It's kind of doing double duty here, and namely what a combination accomplishes is it is a calculation to determine the number of samples that are possible from a larger group, say a population. An important point about that is that this is without regard to order. And we'll specify what that means here shortly. So here, a way of selecting j elements from a larger group of n elements. And we often call this n choose j, or even, if you want to put numbers into it, 48 choose 5. Let's see how we calculate this. N choose j is often written as such, where there's a capital C and a subscript n and j on opposite sides. Another popular way to denote this is it almost looks like a fraction, but it's not. These are just the numbers n, j stacked on top of each other with a tall parenthesis. The formula is n factorial over j factorial times n minus j factorial. Now I realize I might need to describe what a factorial is. Let's do that over here. A factorial is a series of multiplications, and I think I'm just going to do an example to illustrate this, where 5 factorial is 5 exclamation mark, and it's just 5 times 4 times 3 times 2 times 1, and that is 120. Not so bad. Another example of factorial, let's do 6 factorial. That would be 6 times 5 times 4 times 3 times 2 times 1. But we can use some of our previous work. Let's just say 6 times 5 factorial, and that would be 720. So that's what all these exclamation marks are. I have this memorized in my head as big number factorial over small number factorial times big minus small factorial. These numbers can grow quite large quite quickly. Let's do an example that doesn't get too big. Let's compute 7 choose 3. We're going to do the computation, and we're going to discuss how to interpret that. Alright, 7 is the bigger number, n. It's going to go in the numerator with a factorial. 3 will go in the denominator, and then 7 minus 3, and factorial on both values there. Okay, now I'm not going to bust out a calculator yet. I want to see how much of this we can accomplish by hand. Remember, we want to do the parentheses first here. So I'm going to actually go vertical here. 7 factorial over 3 factorial times 4 factorial. With all of these problems, there is a cancellation that is waiting to occur. I'm going to for the moment, rewrite my denominator. 3 factorial, 4 factorial multiplied. I'm going to rewrite my numerator in a strategic way because I am anticipating a cancellation. 7 times 6 times 5 times, here it comes, 4 factorial. The cancellation here are these 4 factorials. That's a fancy one. So all I am left with is 7 times 6 times 5 over 3 factorial. But wait, there's more. Isn't 3 factorial just a 6? Because 3 times 2 times 1. So look what else can cancel here. The 3 factorial with that 6. So all that is left is 7 times 5, which is 35. That would be our solution. Let's interpret this value of 35 being the solution to 7 choose 3. I'm going to draw a few faces here. Okay, I've got 7 faces representing 7 different individuals. 1, 2, 3, 4, 5, 6, 7. Here we've got a larger group of 7 individuals. And basically what we want to think about is how many unique groups of 3 are possible. Well, we could have blue, green, and red individual. That's a group of 3. We could have blue, green, and yellow. That's another group. Or how about yellow, blue, dark blue, and orange? That would be another group. And so on and so on. So here I have identified 3 of these possible groups of 3, but there would be a total of 35 groups, or I should say combinations of 3 possible. So that's what a combination is. It's the number of unique groups that are possible from a larger group of a specified size. Now, earlier I mentioned that a combination is without regard to order. So right here what I'm circling is a group of 3. However, notice it is a simple rearrangement of this group of 3. Yellow, dark blue, and orange. So this is not a new combination, right? This could not be a combination if this one on top already is, because a combination is without regard to order. This is a simple rearrangement of an existing combination and therefore would not count. Unless it was the first one to be counted, then it would be this guy, this set of 3 that wouldn't count. But that's the idea, is this is like a team of players, and this is a team of 3 that has been created, and this is essentially the same team. You don't want the same team twice. Now I want to try this one more time and show you a little cool property. Let's do similar numbers. Let's do 7 choose 4. Seems similar, but it's different, because these would be groups of 4. Let's compute this. 7 factorial on top, small number 4 factorial times 7 minus 4 factorial. Now that we know that there's a cancellation waiting for us, let's rewrite the denominator as 4 factorial times 3 factorial, and strategically rewrite the numerator knowing that a cancellation is about to occur yet again with the 4 factorial. So again, the 4 factorial is canceling, and again we can see the 3 factorial would cancel with that 6, leaving us yet again with 7 times 5, which is 35. So this is pretty cool, isn't it? We got the same answer twice. So let's write down a little property here. Notice that 7 choose 3 was the same as 7 choose 4, and that was 35. The reason for this is because the numbers 3 and 4, they add up to 7, right? Imagine these groups of 3, like up here. Every time you have a unique group of 3, you have left out a group of 4, haven't you? So this group of 3 has left out a group of 4. And the second group of 3 has left out a new group of 4. So these are sort of complementary in a way. That is why these two quantities are equal. Let's look at some other neat properties. What if we did 48, that's how many are enrolled in our class, choose 48. Let's think about it. If there was 48 people total, how many ways can you select everyone? There's only one way for that to happen. That's fun. What about 48? Choose 1. How many groups of 1 are possible from a group of 48? Must be 48. Ooh, wouldn't this also be the same as 48 choose 47? That's kind of cool, huh? I have another one to show you. How many groups of 0 are possible from a larger group? Only 1. Now there are some cool, quick ways to do this on our calculator or on the internet, and I'm going to show you that right now. Here I've got a virtual version of a TI-83, and this can apply to a lot of other TIs in its basic place where you can find this functionality. In this calculator, what I want to do is first type the large number. Start with 48, and I want to get to the math button. Under the math button is a probability toolbox, and in other TI calculators you might have a PRB button flying around somewhere, and that's what you would look for. And when you select that probability box, you'll have functions such as, there it is, TI calls it NCR, and hey, there's a factorial there as well. Let's try 48, choose 48. We know the answer. Awesome. Let's try 48, choose 1. We also know the answer to that. Or how about 7, 7, choose 3. We know the answer there. Now let's have some fun with this. Let's do 48, choose 2. It's going to get a bit larger than 48. That's fun. What about 48, choose 20? This might get astronomical. Let's give it a shot. Woo! Remember what this means here. This says take that decimal point and move it over 13 times. What would that be? Is that 16 trillion and change? Woof, that's good stuff. Another way that you can calculate these, I don't want you to calculate that by hand, that's insanity. But another way that you can do this is on the old Google here. I'm going to go just straight into the search bar. Let's do 48, choose, let's do 23. Even bigger, huh? So hopefully you can use some of these tools at your disposal to save you some time. Let's look at just a couple more examples for the fun of it. How many groups of 2 can you select from A, B, C, D? Let's list them all out and then we'll count them and validate that with the formula. We've got AB, AC, AD, BC, BD, and lastly, CD. Notice that there are no duplicates here in the sense that AA does not count and BA would be the same as AB, so we are not using those. So cross those out. The number of combinations here then appears to be 6, right? 6 groups. Let's look at this second part. Again, how many groups of 2 can you select from A, B, C, D, E? So now we've got the inclusion of another letter here or another object, E. Well, wouldn't it be all of these same groups here? I would need to attach E along with the A, along with the B, the C, that's not it, and the D. So here this would be 10 groups. Count them up. Groups of 2 can be pretty nice to work with. Groups of 3 we start needing to be pretty careful about how we keep track of things. Let's see here. We could have, well, groups of 3 out of A, B, C, D, that's a larger group of 4. Basically every group of 3 I'm going to exclude only one letter. So let's consider A, B, C. We have excluded the D. A, B, D. That time we excluded the C. A, C, D. That time B is out. And lastly, we're going to exclude A, so that would be B, C, D. So it appears here that there are 4 groups. Okay, so hopefully using our reasoning and intuition, we've got our solutions here. And I'm going to utilize the calculator to help me validate these, kind of proving it to ourselves. So here we're going to need to do 4, choose 2, And we're pretty sure that's a 6. We'll double check with the calculator. This here is 5, choose 2. We're pretty certain that's a 10. And this is 4, choose 3, which we're quite certain is a 4. Calculator time. Taking it from the top, let's do 4, math, choose 2, and the answer should be a 6. I think I can go to second entry and be a little lazy here. 5, choose 2 ought to be a 10. And again, second entry, this time 4, choose 3. Are you a 4? Indeed. Hopefully that was fun. We're going to utilize this in a later section in this experience when we talk about binomial variables.